Legendre duplication formula. We are going to prove the duplication formula that is well known in the GammaFunction. So we are going to prove this, and then there are different deductions that has been made from this. Deduction 1, 2, 3, and 4. We are also going to prove how we come about all these deductions. So see what happens. The first thing I'm going to do here is, we know beta of n comma n, that will be equal to, of course, this one will be equal to gamma of n all over gamma of n plus n. This is gamma of n, everything squared, all over gamma of 2n. Let's call this 1. Now, again, from bipolar definition of the GammaFunction, we have beta of n comma n to be, don't forget, beta of n comma n bipolar definition is equal to 2 integral from 0 to pi over 2 integral from 0 to pi over 2 of what? Sine 2n minus 1 theta cos 2n minus 1 theta. The theta, that is what we are going to have, right? So that is what we have. So, but now I want to do beta of n comma n. This one will be 2 integral from 0 to pi over 2. This one will be 2n minus 1, 2n minus 1. So I can group them together to become sine theta cos theta, everything raised to the power of 2n minus 1, the theta, as you can see. So don't forget, this is 2 integral from 0 to pi over 2. If we look at sine theta cos theta very well, this is the same thing as 1 over 2 sine 2 theta from trigonometry of 2n minus 1 the theta. This is from trigonometry because sine 2 theta is equal to 2 sine theta cos theta. So this 1 over 2 we cancel the 2. So at the end of the day, this one will become 2 over. Now this 2 will also take this power, but it will come out because it's a constant. So it will become 2 raised to the power of 2n minus 1. That's what I'm going to have. So I have integral from 0 to pi over 2 of sine raised to the power of 2n minus 1 theta the theta. So to evaluate this or to solve this, we know how to go about it. We are going to, of course, we know how to evaluate this whenever you have something like this from the beta function. Don't forget, this is same as 2 raised to over 2 raised to the power of 2n minus 1 integral from 0 to pi over 2 of, this is sine 2n minus 1 theta. Then this is cos what? 0 theta the theta. So we apply the beta or the gamma by beta and gamma function or the gamma function. This is same as, so it means that beta of n comma n is equal to 2 over 2 raised to the power of 2n minus 1 multiplied by, so what I have here, what do I have here? This one is equal, this is beta of n comma what? Now don't forget from the beta function that whenever, of course, if you look at this one, this is so I have 2n minus 1, so that is n. 2n minus 1 here is 0, so that means n is 1 over 2. This is beta of 1 over 2, everything divided by 2. Right? That is from the polar definition of the beta function. If you put this now, don't forget, bipolar definition of the beta function, that is beta of mn is equal to this. Now change m to n and let n be 1 over 2. This one will be sine 2n minus 1 cos 2 times 1 over 2, which is 1 minus 1, 0. You will get this. then this 2 we cancel. So this 2 that I put all over, don't forget 2 will always be in front of it. So since I did not put any 2 here, so I divided it by 2. So now this 2 will cancel this 2. So you will be left with this 2 will cancel this 2. You will be left with 1 over 2 raised to the power of 2n minus 1. Beta of multiplied by beta of n, beta of 1 over 2 is gamma of n, gamma of 1 over 2, all over gamma of n plus 1 over 2. Now, this is, let's call this 2. From 1 is this, and 2 is this, and they are the same, beta of n, beta of n. So equating the two of them, you have, when you equate it, you have gamma of n all square over gamma of 2n, because as you can see, beta of n comma n is this, is equal to beta of n comma n, which is also equal to this, gamma of n, gamma of 1 over 2 over gamma of n plus 1 over 2. So this is gamma of n, there are 2 of them, square. That means gamma of n multiplied by gamma of n. So one of them will cancel out, so that you will be left with gamma of n here over gamma of 2n is equal to, then gamma of 1 over 2, of course, we know that that is equal to root pi. We've done that before very well. So this is, I've thrown something away. This 2 raised to the power of 2n minus 1. 2 raised to the power of 2n minus 1, gamma of n plus 1 over 2. So let this come here, let this gamma of 1 over 2 come here, and let this one go there. So that at the end of the day, without wasting time, this is equal to gamma of n, then this one, gamma of n plus 1 over 2 is equal to root pi gamma of 2n. Root pi over, I don't know why I keep forgetting, all over 2 raised to the power of 2n minus 1, then gamma of 2n. That is what I have, as you can see there. So I'm through with the first proof, or with the first with this duplication formula. Now let's come to the first deduction. So it is from here they deduce so many of them. It is from here, it is from what we just saw now. They deduce, like this first deduction, number 1. Deduction number 1, I have beta of n, comma n is now equal to square root of pi, gamma of n over 2 raised to the power of 2n minus 1, gamma of n plus 1 over 2, where n is greater than 0. How do we go about this? How we go about this is just simply going to be, don't forget, beta of n comma n is equal to gamma of n all square over gamma of 2n. That is what it is. So what am I going to do now? What I'm going to do now is that I will do something here. This is equal to gamma of n over gamma of 2n multiplied by gamma of n. So what is gamma of, from deduction 1? Now from 1, let us see from 1, from A. From the first deduction, gamma, if you divide through by gamma of 2n, you have gamma of n over gamma of 2n is equal to what? That is from the last thing we just finished now. This is equal to square root of pi over 2 raised to the power of 2n minus 1, then gamma of n plus 1 over 2. That's what I'm going to have when I divide through by gamma, or if I make gamma of n over gamma of 2n the subject of formula. That is what I'm going to have. So it means that beta of n comma n will be equal to gamma of n over gamma of 2n is equal to square root of pi over 2 raised to the power of 2n minus 1 gamma of n plus 1, then multiply by gamma of n, and we are done with the first deduction. So this is purely equal to root pi gamma of n over 2 raised to the power of 2n minus 1 gamma of n plus 1 over 2. And that's all. That's all about this problem. We are done with the first deduction. Let's go to the second one. The second one too is quite trivial. Since we've proved the duplication formula, the second one is quite simple as well. This is what we are going to do for the second one. For the second deduction, for number 2, we want to prove that deduction 2. We want to prove that 2 raised to the power p gamma of p plus 1 over 2, then gamma of p plus 2 over 2 is equal to root pi gamma of p plus 1. So this is what we are going to do. We will let, so this is what we want to prove. So from A, so that means from this place, from this one, you just need to let p to be 2n minus 1. How do I know that is what I'm going to use? Because I can see 2 raised to power p, and this is the only 2 here. So I have 2n minus 1. So let that 2n minus 1 be equal to p. Make n the subject here. By the time you make n the subject, n will be equal to p plus 1 all over 2. So put it in that, put it in this equation. Put it here. So you have at the end of the day, of course, gamma of n is gamma of p plus 1 because I have changed it. Then gamma of n plus 1 over 2, that's gamma of p plus 2 over 2. That is gamma p plus 1 over 2 plus 1 over 2, that's p plus 2 over 2, is equal to square root of pi gamma of p, 2 raised to power p, then gamma of 2n. But 2, we cancel the 2, it will remain p plus 1, that's gamma of p plus 1. So let this 2 raised to power p goes to the other side so that you have 2 raised to the power of p gamma of p plus 1 over 2 gamma of p plus 2 over 2 is equal to root pi gamma of p plus 1. That's what I am going to have at the end of the day. So I'm done with the second deduction. Now let's come to deduction number 3. So for the third one, number 3, this is what I'm going to have. I want to prove that gamma of n plus 1 over 2 is equal to 2n factorial over 2 raised to the power of 2n n factorial root pi. Don't forget, they say when n is in n, that is set of natural numbers. That is when n is a positive integer. So now look at what will happen here. What will happen here is that I will also use this. What I'm still using is this first deduction. Divide through by gamma of n. So from A. So from this A as well, I'll divide by gamma of n so that I'll be left with gamma of n plus 1 over 2 here. That will be equal to, this one will be root pi over 2 raised to the power of 2n minus 1 multiplied by Don't forget this is gamma of 2n over, since I've divided by this is what I'm going to have. This is just like you can see. So this is gamma of n plus 1 over 2 is equal to root pi over 2 raised to the power of 2n minus 1 multiplied by gamma of 2n. Of course, the answer will be 2n minus 1 factorial. Then this is n minus 1 factorial. Multiply both numerator and denominator by 2n. Multiply both numerator and denominator by 2n. So this is equal to root of pi over 2 raised to the power of 2n minus 1. Multiply by, if you multiply this one by 2, this one will be 2n minus 1 factorial all over 2n n minus 1 factorial. So that at the end of the day, gamma of n plus 1 over 2 will be equal to, look at what will happen to this one. This is root pi all over 2 raised to the power of 2n minus 1 multiply 2n multiplied by 2n minus 1 factorial is 2n factorial all over n multiplied by n minus 1 factorial is n factorial, but the 2 is still there. Let the 2 multiply with this, you have gamma at the end of the day. Gamma of n plus 1 over 2 is equal to root pi or 2n factorial root pi all over 2 raised to the power of 2n multiplied by n factorial. 2 raised to the power 2n minus 1 multiplied by 2 will give me 2 raised to the power 2n, and I'm done with the third deduction. I'm done with the third one, so I'm left to prove the last one. I'm left to prove this. So to prove the last one, this is what I'm going to do. So to prove the last one, don't forget number 4. This is what will happen. We want to prove that gamma of n, gamma of 1 minus n over 2 must be equal to root of pi gamma of n over 2 all over 2 raised to the power of 1 minus n cos n pi over 2, where 0 is less than n less than 1. So don't forget one thing here. One thing here is that gamma of n, gamma of 1 minus n, don't forget, is equal to, we recall from the properties, pi over sine m pi. And again, from 1 as well, you can see 1. So I call this one equation 1. Then this one will be equation 2. Just call this equation 2, gamma of n plus 1 over 2, or let me use m is equal to root pi over 2 raised to the power 2m minus 1 gamma of 2m. So let me call this equation 2. I'm going to do one substitution here, and the substitution is that I'll let m to be n plus 1 over 2 in equation 1. Then in equation 2, I will let m to be equal to n over 2. So now let m to be equal to n plus 1 over 2. That is in equation 1. Then in equation 2, in 1, and then let m to be equal to n over 2 in equation 2. That is what I'm going to do. So equation 1 will transform to gamma of n plus 1 over 2. That is what it will transform to. Then this one will transform to gamma of 1 minus n plus 1 over 2 is equal to pi over sine n plus 1 over 2 pi. So at the end of the day, this one will become gamma of n plus 1 over 2, n plus 1 over 2. Don't forget what we want to prove, it is still written up. Then gamma, this is 2 minus n minus 1, that is 1 minus n. 1 minus n over 2, that's what you are going to have here as well. It's equal to pi over sine. This one will give me n pi over 2 plus pi over 2. So, from trigonometry, sine theta plus pi over 2 is equal to cos theta. From trigonometry, this one, what I mean is from trigonometry, sine theta plus pi over 2, this is from trig, is equal to cos theta. So that means sine n pi over 2 plus pi over 2. So at the end of the day, this one will become gamma of n plus 1 over 2, gamma of 1 minus n over 2 is equal to pi over sine and cos over cos n pi over 2. So leave that one. Let's come to the second equation now. So this is let me call this maybe 3. Now let's come to the second equation. The second equation is I said let n be equal to n over 2 in the second equation. So this is gamma of n over 2, gamma of n plus n over 2 plus 1 over 2, that's n plus 1 over 2 is equal to root pi over, I said this to be n over 2, so that's 2 raised to the power of n minus 1, right? Gamma of n as well. Let's call it 4. So I'll divide equation 3 divided by equation 4. Equation 3 divide equation 4. So what is equation 3? Equation 3 is gamma of n plus 1 over 2, gamma of 1 minus n over 2, all over equation 4. Equation 4 is gamma of n over 2, gamma of n plus 1 over 2 is equal to equation 3. I have pi over cos n pi over 2, everything divided by root pi over, or root pi gamma of n over 2 raised to the power of n minus 1. So at the end of the day, see what will happen. This, we cancel this. So I'll be having gamma of 1 minus n over 2 all over gamma of n over 2 to be equal to, then at the right hand side, look at what we are going to have at the end of the day. I have pi over cos n pi over 2 multiplied by, divide, we change to times, then you reciprocate 2 raised to the power of n minus 1 over root pi gamma of n. That is what I'm going to have. So that at the end of the day, I have a gamma of 1 minus n over 2 all over gamma of n over 2 to be equal to, this one will be equal to pi divided by root pi. The answer will obviously give me root pi at the numerator, because this is root pi all squared. So one of them we cancel out, then you will be left with root pi. Multiply by 2 raised to the power of n minus 1 all over, then this is cos n pi over 2 gamma of n. So at the end of the day, to finish this, let this gamma of n over 2 come to this other side. Let gamma of n come here, so that you will have at the end of the day gamma of n, gamma of 1 minus n over 2 to be equal to, then this one has come to the other side. I have root pi gamma of n over 2 all over. So this 2 raised to the power of n minus 1. If I bring it to the denominator, it will become 2 raised to the power of 1 minus n, obviously. So this is over 2 raised to the power of 1 minus n. Just multiply the power by minus. So you have 2 raised to the power of 1 minus n. Then what you will be having before at the denominator is still there, cos n pi over 2. And that is the answer to that question as well. So that is all. So we want to write we want to just do one example or one exercise, one more exercise on this. So on this exercise, I think we are going to be needing deduction 3 or deduction 1. I think we'll need deduction 1. So now let's write something like this. Prove that. Now exercise. Prove that. So prove that what? That beta of m comma m, beta of m plus 1 over 2 comma m plus 1 over 2 is equal to pi m raised to the power of minus 1 over 2 raised to the power of 4m minus 1. Solution. So on the solution, what am I going to be using? I'm going to be using deduction 1. Recall that so deduction 1 of what we just proved, we just concluded now. Recall that what beta of n comma n is equal to what? It's equal to square root of pi. I'm just trying to write out deduction 1. Gamma of n all over 2 raised to the power of 2n minus 1 gamma of n plus 1 over 2. So gamma of m comma m. So this is from deduction 1. So it means that beta of m comma m is equal to root pi gamma of m all over 2 raised to the power of 2m minus 1 gamma of m plus 1 over 2. So I'll do the same for the next one. I'll do the same for the next one. The next one is beta of m plus 1 over 2 comma m plus 1 over 2. So beta of m plus 1 over 2 comma m plus 1 over 2 will be equal to, this one will also be equal to gamma root pi gamma of m plus 1 over 2 all over 2 raised to the power of 2 m plus 1 over 2 minus 1 gamma of m plus 1 over 2 plus 1 over 2. That is what we are going to have. So I multiply them together now. I know what beta of m is, and beta of n plus half is. So multiply them together. Or let me just get a final answer here, or a more compact answer. Root pi gamma of n plus 1 over 2 all over. This is 2n plus 1 minus 1. That's out. So that is 2 raised to the power of 2m. Then gamma of n plus 1. Half plus 1 will give me 1 actually. So the next thing to do, beta of m comma m, beta of m plus 1 over 2, m plus 1 over 2 will now be equal to beta of m comma m, beta of m plus 1 over 2, m plus 1 over 2 will now be equal to, what is this? This is equal to, let me write equal to our denominator, root pi gamma of m over all over 2 raised to the power of 2m minus 1 gamma of m plus half, multiply by the next one. This is also root pi gamma of m plus 1 over 2 all over 2 raised to the power of 2m gamma of m plus 1. That is what we are going to have or obtain. If you look at it very well, root pi multiplied by root pi will give me pi. That is root pi square. Pi we cancel square root. Gamma of 1 over 2, we cancel this, we cancel this. So you'll be left with gamma of m all over, now 2 raised to power 2m minus 1 multiplied by 2 raised to power 2m by indices, by law of indices. By the law of indices, this will become 2 raised to the power of 4m minus 1. Then gamma of m plus 1. And this is actually equal to pi gamma of m over 2 raised to the power of 4m minus 1 multiplied by gamma of m is m gamma of m. Gamma of m plus 1 is equal to m gamma of m. So again, cancel out this, cancel this. So that at the end of the day, we have beta of m comma m. I have beta of m comma m, beta of m plus 1 over 2, m plus 1 over 2 will be equal to pi. If this m comes to the numerator, it becomes m raised to the power of minus 1 over 2 raised to the power of 4m minus 1. That is the answer to this question. So that's all for this lecture. Thank you very much. Please remember to subscribe to the YouTube channel. Thank you.